Welcome back from lunch, everyone. We've got one lecture now, and then the later part of the afternoon is going to be hack time. I'm going to check in personally with all the groups and make sure things are going okay. But for now, we've got a lecture on overlap reduction functions for pulsar timing arrays. There are a lot of hidden assumptions we make in deriving the Hellings-Downs curve. Levi Schult, who is a rising fifth-year PhD student here in the VIPER group, is going to unpack all that for us and show how we can tweak some of that physics.
Thank you. Thank you. Okay, yeah, so overlap reduction functions, what are they? Why do we care? First thing is I just put my tutorial on the GitHub, so you may need to git pull and get that. And I'm hoping that y'all have QPy, and I tried to make it very minimal in terms of the requirements, but it just needs Enterprise and NumPy and QPy. So hopefully that works, but we'll get to that in a little bit. Yeah, why do we care about overlap reduction functions? Gravitational wave signals that we're looking for, right, are very low amplitude. They're very small, so small that we can't just observe one pulsar and observe those timing deviations from supermassive black hole binaries, right? So we need to correlate the timing deviations from many pulsars to dig below the noise and to pull out those tiny gravitational wave signatures. And these overlap reduction functions, or ORFs, include your PTA's response to a given spatial distribution of gravitational wave power. That's kind of in the gravitational wave side of things. I'll kind of talk a little bit about the ORFs that can result from other physics that create timing deviations, but I think it can be useful to kind of understand them in terms of the gravitational wave power that your array is responding to. So a bit, going back a bit, you know, to Steve's talk on stochastic gravitational wave backgrounds from last week, we have our induced redshift on a pulsar. On that top line, we have, you know, the pulsar term is that exponential, the Earth term is that one, and then you have your gravitational wave amplitudes summed with your antenna response function for the pulsar in each polarization. But again, we have to correlate those redshift, those induced gravitational redshifts. And then those brackets, right, we're taking a expectation value of those correlations, right? Because fundamentally these correlations are, or these timing deviations are dependent on the exact form of that HA, that gravitational wave amplitude, the coefficients for your Fourier basis. But we don't know that a priori. We probably will never actually, you know, be able to know that exact form. So we have to build an ensemble of universes that we hope are realistic, and take the expectation value over all of them to say, what are we looking for? What are we looking for in our pulsar timing array that would tell us it's, you know, a stochastic gravitational wave background? So of course this gets really complicated because now you have two pulsar terms and the Earth terms, and then you have their, you know, joint response. But we can remember that we're making some simplifying assumptions in our ensemble of model universes, right? We say that it's unpolarized. That's the delta A over A. Actually, I should probably do this one. Delta A prime is unpolarized. We say that it's stationary. That's that delta F minus F. And that different directions are not correlated with each other. And then the additional final terms are the power spectral density for the gravitational wave power, and also its spatial distribution on the sky. Now that lets us simplify a lot. And, you know, for many of the things we've been considering thus far, we say that the spatial distribution is totally isotropic. So that means it's one everywhere. We'll relax that a little bit later, but this gets us to our kind of final proportion that lets you see where the overlap reduction function comes from in our derivation for the response of our pulsar timing rate to a stochastic gravitational wave background. So it's not too difficult to see, right? We have our sky map of, gravitational wave power across the sky. We're integrating over the entire sky, and then we have the response for pulsars A and B in the plus polarization and the cross polarization. And so that brings us to the Hellings-Downs cross correlation. Right, this smoking gun, this fingerprint of gravitational wave of a gravitational wave background in pulsar timing waves. There's a lot of interesting aspects to it. Again, this paper was mentioned before earlier in the week, but I'll shout it out again. It will probably go into a lot more detail that I can't do today, and has a lot of the math as well, which is really helpful for understanding this. It may take a few reads. I know it has for me, and I probably still will read it again. The Hellings-Downs curve is asymmetric, right? This doesn't totally, I guess, make sense when you think about, the perturbation to a ring of test masses looking the same, wherever you look kind of thing. But this is actually an effect of the fact that we are a long arm interferometer experiment, right? We have many gravitational wavelengths between the Earth and the pulsars that we're detecting these gravitational waves with. And that changes how the array responds to these gravitational waves. So on the left, you're seeing this geometric factor for how an interferometer would respond to gravitational waves propagating along the z-axis. And Pi, Pj are the vectors representing the pulsar position, and then Eij to the A is the polarization tensor. But when you go, and so on the left, this is the short arm response. This is what you'd have for things like LIGO. And the important thing here is, right, like if you reverse, if you put a pulsar on the opposite side of the sky, it's going to respond to gravitational waves the exact same. So there you'd have that exact symmetric Hellings-Downs correlation, right? But if you go to the long arm detector, you get this 1 plus omega dot p, and now there's a preferred direction to how the pulsars respond to gravitational waves. So now you can see that it will respond much more strongly to gravitational waves from the positive z direction. And so this, kind of hand wavy intuitive sense is where that asymmetry comes from. I really, really recommend taking a look at the frequently asked questions about the Hellings-Downs correlation by Bruce Allen and Joe Romano. It goes through this math in a very detailed manner, and there are some other nice graphics as well that show the timing response and that sort of thing. There's also some nice illustrations like this one about what the gravitational wave response is for each of these 6 interferometer setups. Right, in the first one, you're going to have no response as the gravitational waves are propagating down the screen. Right there in GR, right, we have plus and cross transverse polarizations. So as they're stretching and shrinking your ring of test masses, right, you're not going to have any transverse changes in the position if it's going right along the line of sight between the Earth and the pulsar. In the middle example, in this case, the arm length is an integer number of gravitational wave cycles. So now you actually have the Earth and pulsar being shifted by the gravitational waves in equal amount. So you're not going to get any relative Doppler shift in the pulsar rotation frequency. So with that even stretching and squeezing on either side, you have no response again. But on the third case, now we start to have that kind of asymmetrical long arm response where the measurement in U1 going along the gravitational waves is kind of surfing, and you get more response than U2 going against the current almost. Those are just some hand wavy kind of intuitive ways to try to understand the asymmetry. There are some nice plots where they show the response function as you vary the FL over C. This is like how many wavelengths are fitting within your arm length. And you can see that you move from the short arm case to the slightly more complicated long arm case within pulsar timing arrays. Another good question about the Hellings-Downs overlap reduction function is, right, we've started to see evidence for this in the papers from 2023. Like, amazing, we're just gonna like keep measuring better and better our correlations and we're gonna get exactly Hellings-Downs. Not exactly. We have to remember that the Hellings-Downs correlation came from us taking the expectation value over an ensemble of model universes, right? So that's like the mean. That's like the first moment, right, of our model of our ensemble. But the important thing to remember is, right, there's the next mean or the next moment, which is the variance, right? So we need to also understand across those different realizations of the universe, what is the variance in that expected correlation? And these variances, this cosmic variance, is coming from the fact that our sources are interacting, right? So as, if we pick like a random point on the sky, let's say like here, right, you're getting the gravitational wave contribution from many different sources, and those waves being, you know, we have thousands to more sources per frequency bin, those waves are going to overlap and positively and negatively construct with or interfere with each other. So this creates like kind of a fundamental limit on our ability to actually get Hellings-Downs, because we have one universe, we don't have an ensemble of universes to average over and get an exact Hellings-Downs, right? So it'll be something around Hellings-Downs, but not exactly Hellings-Downs. So this is kind of an example of that. So this is from Constanda in 2024, which is a nice paper that has some good explanations of the different effects for variance of the Hellings-Downs correlation. So on the left, you're seeing in the dark blue, you're seeing all of the variance of the Hellings-Downs correlation. And this includes pulsar variance. So pulsar variance, as a brief explainer, is the fact that, right, you could have two pulsars that or you could have a series of pulsars that have the same separation angle. So, right, it should go in the same place on the Hellings-Downs curve, but you're going to have them on different sides of the sky. So if you have it, wait for the GIF to repeat, hopefully. But if you have it on one side of the sky where there's, you know, it's right next to a binary or something, and it's getting way, you know, this pair is going to experience way more gravitational wave power than on the other side of the sky. You're going to get different correlations, even in the same, you know, what you should expect be in the same correlation bin, kind of in the Hellings-Downs expectation. You can kind of get around this by binning your correlations in angular separation. So we can kind of like semi-neglect pulsar variance, but fundamentally we can't get past cosmic variance, which is the fact that, right, our gravitational wave sources, which we expect to be supermassive black hole binaries, will be interfering within the frequency bins we're observing them in. So on the right, you're kind of seeing those, the spread in the, I think it's the dot dash black HD curve there. Yeah, so that's a bit about cosmic variance. That is going to be something that we are starting to take into account, and we'll always have to take into account as we continue to measure the Hellings-Downs correlation in future data sets, and say, you know, it's the expectation. It's helped us kind of get to the point where we're at, where we feel confident in our evidence for a gravitational wave background, but we will never reach that exact measurement. Yes.
Did you fill out the right question?
Yeah, so the left is including pulsar variance, which is the fact that, right, some pairs with the same angular separation will be on different points on the sky. But on the right, they've taken that out, so it's just the different aspects from cosmic variance.
That affects things like K inch.
Yeah, so these four are different contributions to cosmic variance. I think K-int, I think, is the actual integration over the different sky pixels, the fact that your sky pixels will have correlations between each other, I'm pretty sure, but we can double check that afterward as well. Any other questions? So yeah, so that's a bit of some more detail on the Hellings-Downs correlation, but there's other physics that can create spatial correlations across your pairs of pulsars. So we can have monopolar correlations. This is exactly what it looks like, right? You just have some excess timing deviation that you can see across all your pairs of pulsars in the array. So that's that orange line there. And then in blue, I've also plotted the Hellings-Downs curve. And of course, you may have them together, right? That's the other difficult thing about all of these correlation functions, right? Is you will probably have multiple effects in your pulsar timing array at once. So you need to start being able to characterize the different influences that are happening. So here, right, if you had a pulsar timing array that had a gravitational wave background in it, and also these monopolar spatial correlations, you'd have just like some linear offset to your Hellings-Downs. Now this is caused mainly by the fact that in pulsar timing, right, we need to take observations of when the pulses from our pulsars arrive at our telescope. We have to time them and basically sync them with an international time standard, so we're all using the same clock, right? And if you have some systematic error in your time standard that you're referring those observations back to, right? All of your pulsars are all going to start seeming like all the pulses are arriving slightly earlier or slightly later, right? So that means that all the pulsars in the array will have some, timing deviation that's correlated across the pairs all over the sky. So that's kind of what can create the monopole spatial correlations. And in fact, we saw evidence for this in the NANOGrav 15 year. So the solid blue line is the Hellings-Downs correlation. The black dots and error bars are a chosen representation of the spatial correlations. Do not do chi by eye here. Like this, we do the statistics, with, math in the computer, right? Like, it's not just like, it looks like it, but, and then in orange is the Hellings-Downs plus the monopole. And it looks slightly different than the one I plotted earlier, because in the HD plus monopole, the amplitude for the HD shrunk a little bit. So that's why it looks slightly squashed compared to just moving the whole HD up. Now this seemed to be limited to the Green Bank telescope, so maybe there's a clock error there or something. I don't know. I think there's still probably, hopefully it goes away in the next data set is my hope. Because that would say it's a noise thing and not a gravitational wave thing. Okay, dipolar correlations. All right, I just explained to you what can create monopolar ones. There are many things that can create some of these spatial correlations, but I'm just trying to give you examples of some of them to help understand how we can use the overlap reduction function and the correlations we observe to kind of understand what's happening in our array physically. So I will give you a hint with one thing that can cause dipolar correlations. It is again related to our pulsar timing array observations. So what in pulsar timing might make a dipole signature where you have pulsars on one side of the sky positively correlated and on the other side of the sky negatively correlated. Go for it, Lucas. There's no wrong answer. You're trying to figure it out.
I think it's the offset of the varicity of the universe.
That's it. All right. So yeah, dipole is this green curve. So you can imagine, right? We have to offset all of our observations of the pulse time of arrival to a common inertial reference frame, right? You can't just compare the pulses that arrived at Green Bank Telescope in West Virginia with the ones that arrived in the UTI radio telescope in India, right? Because they're on different points of the Earth. You know, the Earth's also moving through its orbit. You don't want the solar system's orbit, you know, and the Earth's orbit to affect our time of arrivals. So you translate them to the center of mass of the solar system using a solar system ephemeris. This is just a model for the positions and locations of masses throughout the solar system. So where's the sun? Where is Jupiter? Where is Saturn, right? Because all of these things are going to slightly offset where the center of mass is. So if you have uncertainties in that center of mass, or the ephemerity, that means that pulsars that you're observing on one side of the sky, when you correct them to the center of mass you think is correct, you know, those ones are going to start to have, you know, so seem to arrive slightly earlier than the ones on the other side of the sky, kind of thing, where, you know, closer to what the true center of mass is. And now, like in the case of our solar system, right, the next largest mass from the sun is Jupiter, right? And so this kind of uncertainty in the solar system ephemeris, you know, masquerading as a gravitational wave effect happened in the NANOGrav 11-year data set. So here what you're seeing in the faded kind of dashed posteriors is the posterior on the amplitude for the gravitational wave background using different solar system ephemeris models. So these are using different models for the center of mass of the solar system. And you're seeing that they all seem to have this bump around -15. But when you know, the thing is people were starting to think this doesn't really make too much sense. It's looking like it has a frequency that lines up with the orbital period of Jupiter, right? So that should tell you something's going on. Also, Steve can correct me if I'm wrong, but it looked dipolar, right? The spatial correlations. So that tells you that it's not gravitational waves, right? So they needed to make some way to include in the Bayesian modeling of the pulsar timing array data, include the uncertainties of your solar system ephemeris. So that's what you're seeing in the solid lines now, is when you include those uncertainties in your solar system ephemeris, this kind of bump in your posterior goes away and it starts to look more like an upper limit, like you would expect. Another thing that can create these dipolar correlations are, you know, like Andrea was talking about earlier today, are dark matter substructures coming, you know, passing the solar system kind of thing that's going to offset your center of mass in a similar way, and you know, create that dipolar signature. So those are kind of some ways that we can use overlap reduction functions to understand quote unquote noise, right? Again, in data analysis in general, one person's signal is another person's noise. So understanding non-gravitational wave effects in our data sets. So going back a second, right, Hellings-Downs comes from the expectation of it fully, you know, it's the expectation over many realizations of the universe that average out to a fully isotropic, the sky is everywhere the exact same gravitational wave power. So we can relax that assumption because we don't, that's not going to be the case. We know that there will be it will be statistically isotropic in one realization. That's kind of part of the aspects of cosmic variance. And we also expect, right, our gravitational wave background is being sourced by a population of supermassive black hole binaries. And naively, one could think that we know from electromagnetic surveys that our distribution of galaxies in the universe is not uniform. You have webs, you have voids of galaxies. So you might think, well, we should have anisotropy from just the large scale structure of the universe, where galaxies are placed throughout the universe. Recent theoretical work has shown that this isn't really going to be the case. It's actually at the percent level compared to what's known as Schott noise. So this is just taking samples from our mass and distance distribution of the population and saying that our anisotropy will actually be dominated by very loud systems. Those could be extremely massive, or they could be just very close. And we'll have to actually beat down that Schott noise and kind of characterize the nearest supermassive black hole binaries before we'll even have a hope of kind of looking at the large scale structure anisotropies. So this is from Steve's paper from a few years back, looking at a population of supermassive black hole binaries and seeing what does their anisotropy look like. So you have, 5 loud systems that are creating these little tiny hotspots on the sky. That's an important feature, right? This anisotropy is pretty small scale, right? That we expect for SMBHBs. So how do we actually model this power? So I'll take you through kind of a little bit of a tour of different bases that we use for modeling P omega. The first, which Steve mentioned last week, is spherical harmonics. This is kind of a basic way to decompose power on the surface of the sphere. You have YLMs, those are your spherical harmonic functions, and then you have CLMs, which are basically the amplitude of those spherical harmonics. So when you're actually doing an analysis, your parameters are these CLMs. Now you of course have to also choose a truncation of this basis. You have to say, what is my Lmax? This is basically the highest spherical harmonic you're analyzing. And the higher the Lmax, the smaller the angular scales you are probing. What you're seeing on the right is kind of some of those basis functions. So you have the 0th one. Here's where things get a little bit confusing because we start to use the same terminology. The 0th mode is also called the monopole, but it's different from, just try to remember that they're different things from the actual monopolar spatial correlation. And then there's L equals 1, which is the dipole, and then it goes quadrupole and octupole and so on. And importantly, there's, I'm going to also explain the benefits and trade-offs of each of these bases, because there's a reason we don't just use one. They all have trade-offs. We have to kind of analyze with each one and know their benefits so that we can have kind of a full picture by using all these bases. So one of the trade-offs of spherical harmonics is that spherical harmonics are not bounded to be positive. You can have areas on the sky that are negative, which is not physical. We expect, there's not going to be negative power on the sky. That doesn't really make sense. So that is kind of an inaccurate aspect of the basis and of the spherical harmonic model that we're using to analyze the gravitational wave sky. The other difficult thing with spherical harmonics is that this is actually cutting off the negative side of the pyramid, but your number of coefficients, your number of parameters for the spherical harmonic model blows up as you go to smaller and smaller angular scales, right? And we're targeting very small angular scales for supermassive black hole binaries. So to solve the first problem, we can switch into the square root spherical harmonic basis. So now instead of modeling P omega, we actually model P omega to the 1/2. So now whatever your spherical harmonic, coefficients are, everything, the entire sky gets squared. So you always have positive power on the sky. Very neat way to go about this. There's some complicated math to convert your BLMs, which are your coefficients on your spherical harmonics, to what you may know of in the linear case. But this works really well. You now have positive power everywhere on the sky, which is great. And this is the sky map in the bottom left is what you're seeing from the NANOGrav 15 year in a certain frequency band. This is another aspect to anisotropy searches, which is that, if we're looking for that small scale anisotropy on the sky from a loud supermassive black hole binary, we're expecting that to be pretty limited in the frequency range, right? Because those binaries will be emitting at 20 nanohertz at some frequency, right? So we should want to look at our anisotropy in particular bins, in particular frequency bins, to see hotspots emerge from individual binaries. So the square root spherical harmonic basis is great. We resolve that physical power drawback of the linear approach, but we are still struggling with the number of parameters, right? It kind of blows up as Lmax plus 1 squared is the number of parameters in your analysis. So if you want like Lmax of 5, and you're not even an Lmax of 5 is not that big. It's not that small on the sky. And you'll kind of see this in the tutorial notebook. You start to get 35 parameters for your MCMC to search through. Also, I'm mainly talking about, all of these things are applicable to the frequentist case, but I have a lot more experience in the Bayesian case. So if you want to talk about frequentist anisotropy searches, Kyle, as with many things, is the expert to go to. So yes, square root spherical harmonics, still struggling with the number of parameters. Oh yeah, and this is what I was talking about with the frequencies, right? As we go to these higher frequencies, the number of supermassive black hole binaries in each frequency bin is decreasing. And so you have these spikes that start to appear because you're having loud systems dominate those frequency bins. So that's why we like to do our anisotropy searches narrow band, because that gives us the best chance of finding, an individual binary through a hotspot, something like that. Yeah, the other thing about spherical harmonics is that, we have a ton of different parameters, and we're working in Bayesian space. Well, even frequentist has uncertainties, right? We have a lot of different series of CLMs that are consistent within our 95% credible region or confidence region. So it's actually very helpful for us to look at the angular power spectrum in the bottom left. So this is also from the NANOGrav 15-year anisotropy search. So here what you're looking at is what is the power in each angular scale, right? So CL, which is these first two, that's basically like hemispheres on the sky, right? And then CL of 1. And then as you go to 2 and 3 and 4 and 5, you're getting smaller and smaller angular scales, right? So you should hope that this gives you an idea of where the gravitational wave power is distributed on the sky. And we have expectations of what this angular power spectrum should look like from a realistic population. So this kind of gives us a way to look at our spherical harmonic results and compare them with what we expect for realistic populations. And I'll show that in a little bit. Again, it starts to really balloon the number of parameters. So we can go to the radiometer basis. So this, instead of modeling power everywhere on the sky with spherical harmonics, we say, if all of the power on the sky was coming from one point, what would that overlap reduction function look like? So here's an example. So I've lit up 1 pixel in the sky. What does that corresponding overlap reduction function look like? It looks like a mess, right? But that's just what that's just what the correlations will look like for this array of pulsars. And so we can use this to kind of say what, what is the gravitational wave power that the correlations we're measuring best corresponds to. So there's two ways of using this radiometer basis, and I'm going to try and define those because they get used interchangeably, and it's sometimes difficult to tell the difference between the two. So the first is the radiometer search. So this says, this is kind of like doing an isotropic search, but instead of your ORF being the Hellings-Downs correlation, you let it be the ORF for that exact pixel, right? So you're saying, for this previous one, if we're searching at that point, we're saying these are the correlations we would expect out of this array of pulsars for that point. If all of the gravitational wave power is coming from that point on the sky and we have our measured correlations, how do they compare to these? And therefore, what is the power in that specific pixel, right? So now we've taken away basically all of the parameters from an anisotropy search, but the trade-off is now we have to do a search for each pixel. So each pixel in the sky, we now have to constrain the amount of gravitational wave power in. So it means a lot of MCMC runs. The other drawback is now pixels are not correlated with one another, right? Because you're looking at one pixel at a time and they don't know about the surrounding pixels. Yeah.
On this correctly, you said that you put all the power into one pixel, and then, so when you're putting all the pixels in terms of that, you feel like small decimal amounts, so that they all add up to one.
Yeah, so it's you're searching one pixel at a time. So you're actually completely ignoring the rest of the sky. So you're basically saying, like, in this case, you're saying, like, when we do this MCMC and we have this map of the gravitational wave sky, we say that all the power that is responsible for making the correlations we're observing is coming from this point on the sky. And if there's not, if the correlations we observe don't really look like the correlations we expect from that point on the sky, then we can say that the power coming from that point on the sky is very little, right? Because it's not really creating the correlations we're observing. Does that make sense? So this radiometer search is one way of tackling this, where you have to do a search at each pixel and say, how much power is coming from, how the power, this point on the sky is responsible for how much gravitational wave power we're seeing. But there's also the pixel search. So this is an example from my own work. This is kind of another way to do it, where instead of saying, let's search for each pixel individually one at a time with a bunch of runs, we instead say, I have all of these overlap reduction functions for every point on the sky. We can just let the data choose which pixels are most responsible. So we give the data all of the overlap reduction functions. We give the data all of these pixels to look at. And then we say, what does the data support the most? So this lets the data say, and the parameters, right, are just the sky locations. So we just say where on, gravitational wave power here has more support from the data, and here has more support, but it doesn't, the MCMC is letting us draw the posterior of the sky location of this anisotropy. So here you're seeing in blue, the SP plus HD method is saying, I'm modeling this gravitational wave background with a single binary injected on top. And I'm modeling that by saying we have Hellings-Downs correlations that, ideally takes care of the gravitational wave background. But we know there is one binary that's loud enough that is on top, creating some extra anisotropy. So we say, let's just say, search where on the sky this gravitational wave power is coming from. And initially, right, the binary is not very strong and it's ill-constrained all over the sky. But as we get more data, the correlations start to really resemble that there's extra power coming from this hot spot on the sky. And that X is marking where the binary is. And so it's honing in on this hotspot of gravitational wave power that is not being modeled by the Hellings-Downs curve, that is modeling the rest of the background. And the nice thing about this approach that we made is that it's in a single frequency bin. So that's what you're seeing in the bottom right, is that it's trying to find not just where on the sky this gravitational wave power excess is, but also what frequency. And so this is kind of why we made it, is because it's well tuned for the binary hypothesis, trying to find an individual one that's in a certain frequency bin on a certain point on the sky. There's also, there's also, I'm not going to go too much into principal maps, but I wanted to introduce it to you because I also wanted to make sure we had time for the tutorial that I made. Principal maps is a way to it's a nice way to kind of get around a lot of the trade-offs of the previous methods, because here we take either the radiometer basis or the spherical harmonic basis, and we perform singular value decomposition. And long story short, it enables you to basically make maps of the sky that correspond to what the array is most sensitive to, right? Because we know that the array should have better angular sensitivity where there are more pulsars clumped on the sky, right? It should be better able to constrain some some binary in between four pulsars that are really close together on the sky, rather than some other part of the sky where they're really sparsely separated. In the spherical harmonic basis, right, you'd have to go to really, really high Lmax to model that kind of power in between those four pulsars. And you'd have to use a ton of parameters. Radiometer basis, right, your pixels aren't correlated. You're not doing like a full search over all the pixels at once in a really agnostic way, I should say. So the principal maps allow you to get around this by saying, I'm going to look at, let's just say, the 9 maps that correspond to the like 90% or something of the array's true sensitivity. So you're truncating like your array's sensitivity in some sense, but you're also limiting it to the ones that it's most sensitive to. So this enables you to model the really small scale and the really large scale at the same time. But instead of parameters on spherical harmonics, you're doing the amplitudes of these principal maps. We can talk about that a bit more later if you have questions, because this is something that I think is going to be used in more and more anisotropy searches in the future. There's a lot of astrophysics we can do with these anisotropies, right? On the left, you're seeing the angular power spectrum for a realistic binary population. This is also from Steve's paper. And you can see it's pretty flat as you go to higher and higher spherical harmonic modes. Other than that, yeah, it's pretty flat. And then on the right, you're also seeing results from the NANOGrav 15 year where it's the square root spherical harmonic angular power spectrum. But you're seeing it across the different frequencies because we did these square root spherical harmonic analyses at the 5 frequencies that NANOGrav had Hellings-Downs correlations in. So, and in the background, in the solid lines, you're seeing realizations from holodeck predicting that associated frequency-dependent angular power spectrum. So you can see that we're starting to maybe put constraints on the actual astrophysics governing the SMBHB population based on this anisotropy. There's also cosmology. Most cosmological gravitational wave signals are isotropic, but just like with the CMB, there should be a kinematic dipole. This is the kind of dipole in the sky that is due to the Milky Way's like movement through the rest frame of the universe. So one side of the sky should be blue shifted and the other side of the sky should be red shifted. And you should see an associated excess and dearth of gravitational wave power on the sky. And compare how this looks to the CMB dipole, right? And some cosmological signals do have anisotropies as well. So those are also things to search for. There's also all of the new physics we talked about this morning, right? Kristen introduced to us the breathing mode, the longitudinal mode, and the vector X and vector Y modes. So these will create their own specialized overlap reduction functions. These are from the NANOGrav 12.5-year search for non-Einsteinian modes. So in the solid blue on the left, you're seeing the Hellings-Downs ORF that we know and love. And then in the dashed line, you're seeing the scalar tensor mode. And on the right, you're seeing the one from the vector longitudinal. And you can see also that the vector longitudinal starts to have really, really high correlation, I think just due to the fact that it's now longitudinal and you start to have things, your pulsars very, very close together are going to have a lot of correlation. I'm no expert in this. Talk to Nima. He led the 12.5-year this paper. You can also do graviton mass constraints via the overlap reduction function. So this is a paper I found very recently that was just looking at how different graviton mass affects the overlap reduction function. There's also Celia Terrell's work as well that I think does this for sub and superluminal propagation velocities. Yeah, I think that's the end of my presentation. So I can take questions now. We can move into the tutorial, which I think is actually the more fun thing, because who cares if you can look at a map? It's way better to make it yourself. So yeah, I'll take questions now and we can move into the tutorial. Cool. I explained everything perfectly. Okay. I'm joking. Yeah, Sebastian.
Showing how sky-localization is evolving over time.
Yeah.
Along with the spectrum.
Yeah.
So at first, it looks like the localization is biased a little bit on the right.
Yeah.
And it also looks like maybe the spectrum was biased with frequency, like right there, you see that there's a two.
Yeah, here it's, yeah, so there's some complicated things happening in the spectrum, mainly that, right, there's gonna be spectral leakage around these frequency bands because you are saying that, we just have some extra gravitational power in a certain frequency band, but really it's not like the binary is exactly on the frequency band center. It's gonna be somewhere in between the two bins. So you can actually have it creates a sync function where you actually have side lobes in the adjacent bins. The other thing we also thought might be happening as well is it sometimes might pick up on the pulsar terms as well. So because overlap reduction functions are not a perfect filter. Like sometimes you can just have your pulsar terms correlate in just the right way, like to get, you'll have excess power, and sometimes in Bayesian, simplicity, it's just easier to put that spike at a slightly lower frequency band. Spatially, yeah, it can be really tied. It can get really sucked into certain pulsars antenna patterns. So that's why you're starting to see this kind of like lobe off of this one pulsar at like, I guess that's 10 hours-ish or something. So like, that's the other thing to notice in this as well, is this was simulating like an IPTA data set. So pulsars are being added at each year once they, at each data set as they reach 3 years of timing data. So those additional pulsars are helping constrain where it is on the sky as well. So it's very noisy early on. We're at 36 pulsars. And then as we start to get pulsars in different regions of the sky, this was actually in what we thought was going to be the bad region of the sky. But it ended up being better. So you can talk to Steve about that. I mean, that caused a lot of headache. But we started getting more and more pulsars in this sparse region that could localize it to within them. Yeah, I don't know if that answered your question. Okay, well, let's move into the tutorial. I think You all should have it under week 2, day 1 tutorials. But this will kind of take you through some of the things you just saw, but you actually get to get your hands dirty. Let me. So, it should be self-explanatory. I've tried to write in a lot of the explanations, but there are just kind of like certain lines where you need to fill in the blank kind of thing. And yeah, just go for it. And if you have questions, feel free to ask your neighbors. But this should give you a good sense of what do the spherical harmonic bases look like? Why does the number of parameters really blow up as you get to smaller angular scales? And yeah, how fun the radiometer basis is. Does it work? Does it import everything? Great. Okay, cool. Well, yeah, we can just do the tutorial for a little bit. Yeah. You may have to get full, but I'm putting on right before the. Okay. Does anyone else have any MPI error?
Yeah. I had that in but I think it was just a little bit in the right environment and like source back to the.
I think it's just because the MCMC is trying to look for this curl very possible, but you don't need it for this, so I'm trying to think of here. I did do like I had to do a basic camera, but also like a bunch of people have this one, and I'll just avoid the shade. So you can comment it out for now. If you have the MPI error, just comment out the PTA-MCMC import out for right now. I thought PTA-MCMC would be part of the installation. Is it not? It should be, right? I don't know. But comment that out for now, and worst comes to worst, I'll upload an actual chain, and then y'all can just read it and pretend like you ran it. Let me message Matt or Nima.
PTA usually has exception that 4 times as well.
Who is having the MPI issue? Raise your hand. Okay, Liana, Lucas.
Oh, so it's still. Oh, so that's fine. Yeah, it's still. Yeah, go back in front. Yeah. That's all.
Yeah, I don't think.
Yeah.
I didn't think it's a problem. You know, it's either.
Okay.
You can.
Oh, you're. Or that or does it have that or that it has
Have you restarted this whole like precursor versus thing?
There may be a way to just like UV PTAs.
I wonder if you could really, how, so, that, or if you can just do, like, you can try to resolve. Yeah.
Does anyone have questions or?
Just wanted to. What is it?
Yeah. Yeah. So the key is our that he is located. So yeah, so here the yeah, so you are and good.
Is there this, or do you need to revise?
Because so this is a way that you can numerically calculate or from a given sky given loss function, which is just your basically and then because the polar term be correlated across the sky, so you basically just add, you just double your final equations, like in like either polar, then at zero angular separation, you get it. Not because it's like just the normal division, but you get double what you should get. Just
Yeah, so for me, everything. So it's anything that's not. So I'll be able to.
yes, I don't want to need to do it every time you increase like the. But I don't even, I've never usually, but. What is the approach? Well, when I then you yes, just you saying that's.
You want to, you can have time to restart. The more you can start it up, it's using full version.
What is LSS?
That's my.
Yeah.
Yes, give me 1 second to this message, please.
Yeah. So, in mind, one thing I is at hospitals. Just the right. Not get hard. You can't even talking for enough. It's all about now. Power cycles. And so. That's our. This is also an. Oh, yes. Oh, my gosh. Sorry.
I'm gonna probably just put in the Slack, because that's probably easiest for you to download it and move it into place, but, I'll put it on the GitHub after, but I'll put it in the Slack right now. Samuel, it's in the GitHub, or not in the GitHub, it's in the Slack, but I'm about to put it on the GitHub.
Yes, yeah, that's what I'm saying.
Steve, can you merge my?
Yeah.
Yeah. Yeah. Yeah, so it's whenever, but we have to basically the last one. So this response is. So you don't have a lot of people. Or I still think, because that's what we created, so that's now, so this is now n pixels. So when you do this, now it's doing n folder by n folder by n bits, and then that n pixels being folded into an all one map. Yeah, well, yeah. Yeah, and then that kind of, that math basically is just around, I just put it in a function in the next. So you don't need to. Or I think. No, oh, this, you're just, I'm just saying, I'm gonna do a single. That's the difference. Yeah, so we can try. You drive, yeah, it's not perfectly level. Yeah. But if I follow. Yeah. Yes. Then it goes. Now it's not. It should. Yeah. Yes. That makes more sense. There. Oh, work, bro. Okay. So the. Oh. Great. Yes, that makes sense. He said it really is because more time, more buying to separate. And that he, he's saying that the everyone is doing, he doesn't think because if you vary including, like when it's obviously. If you shrink the vessel, you don't have those three similar to. But
Yeah. There's so strong performance. Yeah. But yeah, but it was. Just even well, or. Right, so one minus. This. Oh, yeah. Yeah, so. Yeah, so. Here's just, so. So. That there, sorry, basically. Yeah. So. The atmosphere is within numerically. So we have no response functions and all our. And it's very. You found that.
Yeah, yeah, you're right.
I mean, that's probably like this.
Okay, you don't have to see the difference, so you can see the difference, you will. Smart.
Yeah.
It's just the, yeah. Okay. Yeah. So. Run that later. The, or, our response functions are the calculated here, just by doing.
Right.
Plus, process.
Yeah, it's huge.
And the all, all your majors there. Steps are on capital across the line. The next thing is this all becomes. So R is N polar, but N polar, five and ten.
That's.
It's a normal where it's gonna be where it's gonna be your correlations for one polar array, right? So then we need something that's difficult, so we have to sign that something just fully in the cross that difficult. Then you have your order for that side.
Yeah.
So we have our.
So you read this.
So here, what we're gonna do is we're gonna use, our, sky that we made, that's what we use, so.
Here's 0.5.
Here, what we. There you go. Yeah. Yeah. So that.
The compost name is family. So you're bringing.
Right. Yeah. It's fine. Yeah.
No. We saw that.
Yeah, so if you want, you can actually, so the one thing I did. Yeah. What we can do is we can say. Or. Yeah. We can do Yes, now what it's going is, the reason I did absolute is because your also right in responding, but your also very positive there, negative. Right, so to make a map of your first term response. You want to not have your positive and negative correlations cancel each other out. Right? Yeah, that's just a plus A plus, plus B, sorry, F plus A, F plus B. And then plus F cross A, F plus B. So now we made this now. Now you can just, illustrate this shape of that. Okay, we'll just. Yeah, I wanted. Sorry, no, I wanted because.
Yeah.
Now.
You service, that's one of the other times, and then we'll call water. We know possibility.
Yeah, there's something in stable. So, okay, but now watch this. Now we come back up. So we get.
So. It's kind of better.
Yeah, you don't do it all next straight to like 25 or like 50.
Yeah.
Yeah, but I never know you. So now let's just do the first one.
Okay, is everyone having fun making maps? Woo, map making. Okay, okay, so I actually wanted to show something I realized I should probably have put in there. So I think, has everyone made the Hellings-Downs curve from the first few cells? Okay, so I wanted to give some intuition for what the for what that response matrix is, which is n pulsar by n pulsar by n pixel. Right, a normal ORF is just going to be n pulsar by n pulsar, right? Because you're thinking for each pulsar, I want to take that and get a correlation value between those two pulsars. The fun thing is that there's a way that you can look at that response matrix to get an idea of where your array is most sensitive to gravitational wave power. So this is of course kind of like a geometric sensitivity. It kind of is ignoring your pulsar's intrinsic noise. Obviously, you know, pulsars have different noise attributes, so some may just be more sensitive than others. But geometrically, how do they respond? Okay, so you can see my screen. So here, what I'm going to do is I'm going to limit myself to only the first 3 pulsars. Hold on here. Okay, obviously with only 3 pulsars, you don't get a lot of correlations, so that looks not great. But the fun thing that we can do is we can make a map of our response matrix. It's important to remember, right, that our pulsars can be positively and negatively correlated with one another. So what we need to do to just get a raw kind of geometric sensitivity is we need to take the absolute value of those correlations to make sure that the positive and negative correlations don't cancel with each other and make it seem like it's not sensitive in one region when it is. So what we'll do is we'll sum over the pulsar axes and we'll take the absolute values. So we'll do one. Verify that it's the correct shape. And now what we can do is HP.MolView. There's a reason there's a rotation equals 180 in all of the mol views. For whatever reason, HealPy just has an offset between the conventions that we usually use. So it's important to include that when you plot the pulsars. Oops, forgot to call the pulsars. Okay, so now you're starting to see like actual antenna patterns on the sky where the pulsars are. So this is kind of like, I've limited it to the first 3 pulsars so we can actually kind of see what's going on. When you have all of the pulsars on there, obviously all of these add, and it becomes harder to make out individual antenna patterns because you have so many pulsars in certain regions on the sky and it's following the galactic plane. But did anyone have any questions? I think we're gonna do a break and then hack time.
Yes.
Yeah. I'll also put this on the GitHub as well. Yeah, you can make this for the whole arrays or response matrix. I just did it limited to the first few pulsars so you can actually see some of those antenna patterns. Were people able to do the MCMC? Okay, that's totally fine. If you want, you can keep working on it, or if this isn't your cup of tea, I won't be offended. The directory may need to be is made by the sampler when you did you run the MCMC? Oh. So if you run the MCMC, it will make the directory that will hold your chain of parameter values, and that should let you look at the chain and do a very basic pixel search. Any other questions? We can move into break time where people can keep working on it. Okay.
Yeah, segue into break time, if you have a question, that's you must be by, otherwise, it's fine. break slash hack time now for the rest of the day. I'm gonna try to walk around and just check in with different teams, see how things are going. This is the list of streets. This is what they have. Now, and this is doing work for you. Art and education. And I'll take it. It should. Yes. Just take yeah. Okay, sorry. Yeah, so this is kind of like getting you each year. This is kind of way to introduce you to how you make products. It's way easier than some, amazingly, you have kind of noise. You have a white noise and you have. It's incredible also. Yeah, this is like kind of the incredible thing about it's they made it so you can look at all these. It's like, yeah. So you're getting like your first value and this is okay, we have it on zero. Yeah, so. But yeah, so. So I have to. Yeah, this next. Yeah, the price of a lot of stuff, like in the background. Yeah, and like, what I'm trying to do here, like, that I showed this is, there are things in the presentation that make things really easy to look at. So like, there's like a white noise block, red noise block, common red noise block, and those ones is just like, give them this, give it the word, and it'll just be. Okay, so this is printed on I'm hoping it, I hope that, I mean, it worked for me. Hey, turn off the burning lights.
Yeah, so your burden is normally like 25%. And you can say, you can just say like. No, so I think just do here, just put it in with your. Yeah, and so now you sort of see this. I mean, there's something about it more, but it's. So now just, yeah, put in the burden. This stuff is just showing, I mean, this is just showing that you just have not, you have a statistical way, so it's not gonna be exactly sure. Right. That's stuff that you can really find that variance, that's not even like, it's just like, here's my mom, because I don't think it's true. Yeah. Yeah, so. Yes, so this is actually an amazing part of it. So our model rate is white noise and that's a match. It's, I mean, like, it sounds like it should be more much. See, right, I'm reading it for this, yes. Yeah, you have, I'm probably right. It's, yeah, this is just a getting. Yes. Yeah, it's saying, yeah, your problems.
Yeah, well, actually,
Yeah, so the, for the function grade, more like a grade, instead of using start, is that number the last? It's stop, but it doesn't start. So you have to go 30. Yeah, you started reading different. But you mean this thing. Yeah, that. There's no difference.
yeah, I just, yeah.
You know, so it's a much better. This is the, step, so having just a very line, all right? Yeah, so that's how it is.
Yes,
So you can always find many stuff like so you want to be that they reaction just gone through. Get their financial. No, by that, it's exactly, it's a start of a loop. So you can stop the. And also, then you can work. So if you ever need any kind of. I'm gonna try. Just me. Right, and that is not. It's not amazing, it's, Next thing is all. So these are. It has been today.
I'm powered rotating that from. Or even. Jenny. Yes. Which is what we generate at odds. Yes. Yeah, it's okay. We'll figure this out. So what can we do for delicious? Go. And this is what you get something that's really thought up. We'll go.
You only need Really brown.
That's, and then we do the background and that's what I understand. They consider that.
I did a search. And I have.
Yeah.
Yes.
Yeah.
A lot of that is trying, well, it's, yeah. So this, I think this. It keeps saying, violating that. That's an example. Yeah. It's a little bit of that. So we, so. Just
We can also do it in that's also probably. So we can put it out on,
So. That's a.
Okay, so.
Yeah, I figured we could the poster here. Yeah.
Take some correlation here and just look for find something right because so using this kind of thing.
Okay.
And then see see which points best match. You may not even work a full so. So that should let us get the correlation to be like if we have examples. Or if we have my source of. Okay. We would not, and it's like, just say. We have a fixed source gas and areas. All the fix and then we just light up those comments. Just see if we can get anything of that. And then this is like. Marvin, something related to the. Okay, so it's in. Right, so. Is, what do you want to do there?
Just how we do taxes.
That was just. And then just. What you heard. It goes. Then you react and you do the marginalization. Yeah, let's just do the version again.
Okay, that's just like, kind of, it was trying to see us. If you have a non-isotropic system here. Like, could you just assume prior to that? Yes, and prior to you have. And the prior one, they. Part of that, you need to go for it. And
Yeah. So, the idea just now, based on the, was you can't see, take standards, your cultivation, and, figure out what's what it wants to, so that is that's an action.
Yeah.
Wait, box, no, that's
Yes.
I was based on the grading.
yeah, I was thinking, let's be more.
I think that like.
Okay, so one time, there's a lot of reasons about the county wants to be. And they want to. There's a single side of the same. I think there's some.
I think so. I mean, are you thinking like MCMC runs or just best for? Maybe or that's different. Just let it. Will it struggle to bring? Like I guess we should give it actual fine, it is not fixed. Choose this rule. As I mentioned, so we give by, so pixels are numbered like 0, 1, 2, 3, and it like wraps around it, right? And so imagine if it gets a minimum here, really. I mean, I don't know how they measure, like if you have to wrap around like 1 3 to get one pixel over. And so I think it can be 5 data pass. Is then and it's 2 parameters, but.
On the surface.
There's also the. Yes. You buy pixel ordering, but.
Well, the thing is, this is. Yeah, you can do that, so.
Yeah, so this is the original. So then there's also. That's been nested, right? So I'd say there's a new line there. So are you? That's good. I'm gonna take a call. The green team.
Yeah, we. I agree, that's like something they had kind of. I was like, let's all try to, and we're together, but independently, like, struggle on to see if you can have whatever. And it was like, see how we get, and then how we done. Yes. Yes, I do, Lamb has gotten to, or you get, you guys now. I think, I don't know, they just said that, all I think we got the research code and, we had not really come up to speed in a while, so that way. Yes, pretty much, but it's all the two of us, well, yeah, the presentation. Yeah. Yeah, no, I understand that, I'm just saying, so maybe, we'll try to get up to speed. See how I have this. Yeah, so, yeah, things that are doing wrong with us. It says here, I guess.
Well, this was all. Trying to get it right.
Very short, so. So we did successfully. He was on. So, okay, let's forget this stuff. I'll show you one, and my service to use. This now.
That's fine.
Yeah, it makes their noise just. Makes them. This is considered. You was kind of written and most. This is your station. It's just loving that for everyone in that I'm used to.
Yeah.
And then you will have that meeting will have unique. I then so then I really there, I have same rounds. But so I did that while I was proving I mean that and something like that. So our like we have so let's see your lunches and see. So the phones here is just shooting that. Right, every time it goes to the next one, they see a spot and the so on the first one, I policy. See 2000. This is the background. So the reason this is trying to interval times and
And so then those. And then you should not. We are. And the reason why. As long as that's what they. I'll be able to and so we'll probably go. So. I think the thing we want to do, something that is for money, but then something that. Yeah, partly, you know, you would be able to. So that would be and somewhere we're, you know. See those grow.